going to continue with some examples today, and also next lecture, and of course we're going to conclude the chapter on Tuesday, and we're going to have our middle term on Thursday next week. So yesterday we look at an example to determine the voltage and currents inside BJT, and so by looking at by applying a different voltage at the base, you saw two examples. One is that the circuit is in active mode, and then the next one, when we increase the base voltage, it becomes in a saturation mode because there was too much current into the base. Or in other words, there's not enough current in the collector to make up that big beta. So beta becomes small. Maybe we can just go back a few slides, just take a brief look. This was circuit initially was 4 volt, and we found the current of 1 milliamp at the emitter, and we found the voltage at the collector was 5.3, and the voltage at the emitter was 3.3. So the VCE from collector to emitter, the difference is like 8.6 volts. So that's much more than 0.3 volts we needed for active region. And this result was because the base voltage was 4 volt. And from base to emitter 0.7, so you got the voltage over here, 4 minus 0.7, and you got the voltage 1 milliamp at the emitter. So that was easy to calculate. When we raise the base voltage to 6 volts, so what we did was we assume it's active, and we start to look at the current. Now, because it's active, you see that this is going to be 5.3 volts instead of 3.3 from last example. So therefore, IE is a little bigger. And IE is bigger, which means the voltage drop at the 4.7 kilo ohm resistor is also going to be bigger. Therefore, VC is going to be lower. So now you use VC minus VE. What we got was actually negative. It's impossible. That's a condition will never exist. So therefore, our assumption was wrong. So we had to move forward to revise our assumption, saying actually it is in the saturation mode. Now, when it is in saturation mode, the calculation is slightly different. So what we're doing is, of course, we can still get the emitter volt current by looking at 6 volts minus 0.7. We got the voltage over here. So we have the current of the emitter. And once we have the current of the emitter, because it's in saturation now, so VCE becomes 0.2. So from this voltage, at VE plus 0.2, we get VC. So 10 volts minus VC is the voltage difference applied to the 4.7 ohm resistor, 4.7 kilo ohm resistor. Therefore, we can get IC. So now you can see IC and IE is going to be a big difference between IC and IE. And also from there, you can calculate IB, which is the difference between IE and IC. So IE minus IC give you IB. Now use IC divided by IB, what you get is a forced beta, which in this case only 1.5. So we have 2 operation modes. So the next one we're going to look at is we continue to change the base voltage. So instead of connecting to either 4 or 6 volts voltage, now we connect to ground. Can you see what happens now? If you connect to ground, which means the voltage between base and emitter becomes like 0, because there are 2 grounds. So there's no voltage at the base, which means VBE is going to be 0. So in this case, what we found is VBE is going to be 0. So therefore, if VBE is 0, then everything is 0. So it's in cutoff. So IC, IB, and IE, they all equal to 0. And in this case, you can easily find VE is going to be 0 volts as well, because VE now is connected to ground through that resistance, but VC though is going to be 10 volts. So the reason VC is 10 volts because there's no current. So therefore, the voltage drop across that 4.7 kilo ohm resistor is 0. Therefore, so VC is 10 volts. So this one is fairly simple to get. Now, to make that circuit to work, you can do other different arrangements. Now, next example, we're going to look at this one. As you can see here, this is a PNP type of transistor. So when we get the circuit, be careful. If you start by looking at, oh, this is 0, and this is going to be like a minus 0.7, and you did it just without looking at the direction of that arrow. Actually, you're going to make a mistake, and eventually say, oh, it doesn't make sense. What's going on, right? So we look at, first of all, this is a PNP. So for a PNP transistor, we no longer use VBE, but actually we're going to use VEB and VEC. So those are the symbols we're going to use. So VEB and also VEC. So in this case, if you look at, so look at step number 1. Because base is grounded and that emitter is connected up to 10 volts and the collector is connected to minus 10 volts, each through a resistor. So first of all, I think we want to make sure that this circuit or this BJT will not be cut off. Okay, that's something like often we start with to look at whether it's in cut off. If it's in cut off, it's not worth us to do any manipulations because it's going to waste of time. So why is it not in cut off? Well, you can say if it is in cut off, the current will be 0. So if the current is 0, then like what will be the voltage at the emitter? If it's in cut off, what is the voltage at this side here? 10. So if that's 10, but base is 0, that's not possible because you cannot have 10 volts across emitter and base and a PNP transistor. So which means it's not going to be cut off, right? So simply this, I mean, you can certainly write down, but since we know it's not in cut off, so we're going to continue with our calculation. So it's not in, but we don't know whether it's in saturation or whether it's inactive. So we still have to start, right? So we're going to start looking at assume it's inactive. You can also assume it's in saturation to start with. Both will be all right, but of course, eventually we need to verify which one is correct. So let's assume inactive, and then our VEB is going to be 0.7 volts. So therefore, our VE, so how much will be our VE? VE basically is going to be just VEB, so that's 0.7 volts. And therefore, we can calculate IE equal to V plus minus VE divided by 2K. So it's 10 minus 0.7 divided by 2. So that gives you 4.8565. .5 milliamps. Now, because the beta is infinity in this case, so we can say that IC equal to IE equal to 4.65 milliamps. So therefore, now we can calculate our VC. VC is going to be V minus plus RC times IC. So that gives you minus 10 plus 4.65 times 1K. So that gives us 5.35. So it's minus 3.5 volts. So next step, we're going to look at VEC to see how much is it. Going to be VE minus VC. And VE we found was 0.7 minus 5.35. That gives you, which is larger than 0.3 volts. So we conclude that it is in saturation. So we did it all right. Now, if you start with, it's active. Sometimes it can be confusing when you switch from MOSFET to BJTs. Okay, so it is inactive, which is good. Now, if you started by assuming it's in saturation, you will have a wrong answer. And then you would go back saying, okay, it's wrong. Now we need to do it in active mode. So that's, now finally, we want to calculate IB. Now, because IB, so IB will be 0 if you assume beta is infinity. But if you assume IB is like 100 to calculate it, and this often happens, we assume beta is infinity, calculate the biasing point, and then we come back to calculate IB. Sometimes it seems like a little bit tricky, a little bit awkward. Okay, you assume it's infinity, now you calculate everything. Now you go back to calculate IB, assume beta is 100. Well, this is the reason because the beta is so big, it has very little impact in terms of difference between IE and IC. So that's why those two numbers are very close, like 1% difference. But IB is needed in many of the follow-on circuit analysis. So that's why we want to go back to calculate IB. So you would simply use IC over beta, because IC is 4.65 divided by 100. That gives you 0.0465 milliamp, or in other words, it's roughly 46 microamps. So it's not a very small number. So this is a step-by-step solution to the problem. We're not going to stop here. Okay, so another example, this example is actually a slight different arrangement from the previous one. So the previous one is, the previous one is the PNP, but this is NPN now. Remember in example 6, like 4, 5, and 6, we had the base connected to either voltage or ground, but then we have resistance at the emitter. So now this circuit actually does not have a resistance at the emitter, but it has resistance at the base. The procedure is going to be the same. So we can look at how to solve this problem. Well, first of all, this is not in cutoff. Again, it's very simple, because if it is in cutoff, the current in IB will be 0. Therefore, you will get a voltage at base will be 5 volts. And your emitter is grounded, so base emitter will become like 5 volts, which is not possible. So it is not in cutoff. So that's the first conclusion we can make, saying it is not in cutoff. So if it's not in cutoff, we can say that VBE is going to be 0.7 volts. Right? And therefore, we can calculate IB equal to 5 volts minus VBE divided by 100K. So the 4.7 divided by 100 becomes 0.043 milliamps. And so 4.3 divided by 100, yeah, so 0.043 milliamps. Now, since beta was given, so now we can calculate IC is 100 times 0.043, that becomes 4.3 milliamps. So by this time, we can also calculate IE, but let's leave IE later. So we can calculate VC now. So VC will become 10 volts minus RC times IC. That becomes 10 minus RC is 2 times 4.3, so that's 8.6. So that's 1.6 volts. Um, 1.4 volts. Sorry. So here we need to verify that VCE is going to be VC minus VE is going to be 1.4 minus 0 equal to 1.4 volts, so which is larger than 0.3 volts. So it is inactive. So this step is quite important. It's saying that we started with assuming it's active, and finally we verified that it is inactive. So this is very important to close loop. So by this time we can calculate IE now. So IE will be, I'm not gonna spend time on the numbers, but you can find the exact amount of IE by looking at. So, okay, so this is the final solution. Okay. Okay, so now another example with PNP. So again, this is a PNP. I guess the step one is we need to verify whether it's in cutoff or not. Again, similar to the previous examples, this is not in cutoff. Why? Because if it is in cutoff, then VE will become 5 volts, and then VEB will become 5 volts. It's not possible. So sometimes I need to write it before, but this one I just want to write it as an example for you guys to look at it and say, okay, if it's in cutoff, then you got a VE is 5 volts because current is 0, and you got VEB going to be 5 volts, which is impossible. So therefore, it got to be in either active or saturation. So the second step is we're going to assume in active. So we're assuming the active, then VEB will be 3.7 volts. And VE will become so this problem actually becomes a little bit more difficult if we don't assume beta infinity, because VEB is 0.7. But if you look at the circuit, the current flowing from VE to VB, and then it's like you have a current flowing down here, and then you have flow to VE, and then you have flow VC. But each of this one has a resistance. I mean, this one, you guys, if you wanted, you can do equivalent circuit. So you look at the current going from VE down here, and out here it's going to break. And one with a voltage drop goes to this side, another current goes to VE. So now we only know the voltage over here. So we really cannot find the voltage drop across this resistor and across this resistance. All this resistance, there's no way we can find it because the voltage difference is between the two terminals. So if we have to do this problem precisely, like using beta is 30, then we will have to do quite a bit of calculation. So what I want you to do, let me see if I got the slides ready for next slide. So what I want you to do is by assuming, now next slide, we're going to do the real like accurate calculation. So we're going to assume beta is infinity, and then we do it. So if we assume beta is infinity, what we're saying is we assume beta is like IB is 0. And if IB is 0, and then VB, and then VC becomes what? So VB becomes 0. So VC becomes 0.7 volts. And then IC becomes 5 volts minus 0.7 divided by 1K. That gives you 4.3 milliamps. Oh, no, not VC, sorry, VE, IE. This is like a PNP, so this is VE. And then, so VC, I guess next step 4. So VC becomes minus 5 plus 10K times 4.3 milliamps. And this is going to be something like a 4.40, what is it? 43 volts plus 5. So this is going to be 38 volts. So which you can see here. I just want to quickly go do this. You're saying, well, if this is the case, it's not going to be possible. So you get really, VC is like so big, it's going to be 38 volts, which is impossible. So our assumption is wrong. So how are we going to do this problem? Is we have to write the loop equations. So instead, what we're going to do is say we are going to assume a few things like VE here, VB here. So because we don't know VB, so we're going to assume, so we're going to start with assume like a simple VB. Well, that number we don't know. Okay, so because we don't know the current at the base. But if we assume VB, and then we can say IB is going to be VB minus VB divided by the 10K resistance, right? And then we can also, so that's 1. And then number 2, so number, oops, what happened? Then what number 2, we have VE equal to VB plus 0.7. Again, that VB is not known, so it's okay. So we just leave it like that. But now we can calculate IC equal to 5 volts minus VE divided by 1K. And so 5 volts minus VE is VB minus 0.7 divided by, why? This is keep moving. Divide by 1, that gives you 4.3 minus VB. So we got another equation here. So this is like our second equation. Okay, step 4. We can yeah, go ahead.
We now solve for VB because there's a relation between IB and
Yeah, we cannot solve for VB yet because we don't know which IC. We don't know the value. So we still have two variables.
Well, we know that IC equals I well not IC IE. 'Cause
IE,
this
yeah, this is
is
IE.
emitter.
Yeah.
Doesn't IE equal IB over beta?
So yes,
And then we can plug in our two equations that include in terms of VB and just solve for B.
you're right. So at this point, if you assume it's in, like assume in active, and you would say, okay, so IE equal to beta, alpha. Oops. Beta plus 1 times IB. Okay, so that's number 4, right? So, and then we plug in this equation to here. We should be able to, and also of course this one here too. We should be able to find VB and IB. Unfortunately, if you actually continue to do that, you'll find the same problem we had from the last slide, is that actually that we see is going to become so large that it's not possible. So probably I'm just going to just saying I'm going to neglect this step. I'm going to go right into saturation. So everything in saturation, then we have VEC saturation equal to 0.2 volts. And then we have VC now equal to VE minus 0.2, which equal to, and earlier on we said VE was VB, so VB plus 0.7, and then minus 0.2. So it becomes VB plus 0.5 volts. So that's VC. So now you can calculate IC equal VC over the 10K resistance, right? So you can get that equation here. No, VC minus 5, right? So we see minus or plus 5 volts is the voltage drop across 10K resistor. So we got this one here. So now you have a couple equations that has, so you can plug in this one here. So it's going to be VB, plug in that VC becomes VB plus 5.5 divided by 10K. And then, so you see here we have IC, we have IB, and then we have IE, we have all these equations. And then we put them together.
So if we want to find
We want to find a VB basically. So but okay, so IB, the final equation will be IE equal to IB plus IC. So you can see IE is, IE we found was 4.3 plus 4.3 minus VB. 4.3 minus VB equal to IB is, where is IB? Yeah, we need also to write down the equation for IB. I'll write down here. So IB is going to be VB divided by the 10K resistance. So it's going to be VB divided by 10 plus IC now is VB plus 5.5 divided by 10K. So from here we can find VB. That's 0.1, 0.1, 0.2. So what I found was VB is 3.13. So VB is 3.13, and then you can plug in to get IB, IC, and IE. So these are the numbers, I think, yeah. So these are the numbers. So we found IB is going to be 0.31 milliamps, and IC becomes 0.86. What I want to illustrate, of course, IE can be found as well. IE was 1.17 because IE is IB plus IC. But the most important thing is we found beta, which is first, which is IC over IB. That gives you 2.8. So this is the important conclusion we made, is that this beta is very small, much smaller than what was given as 30, yeah. So, but you can, I mean, so this is the more accurate way to do it. But remember, early on, we assumed beta infinity, we did the stuff, and we found that one assume it's not possible in active. So from this point, there's also a simpler way is to assume like saturation. I just want to do this as an illustration, and also if it's assume it's in saturation, like there's a problem because if it is in saturation, we can no longer assume beta is infinity. Really, that's the key, because only active beta is like 100 and so on, so it's bigger, right? So if it's in saturation, you can no longer say that beta is infinity. So therefore, we still have trouble like getting really the relations. But the only conclusion you can get from here is VEC is 0.2 volts, and VEB is 0.7 volts. So that's the conclusion you can conclude from this earlier calculation. Now, since it's in saturation, so beta is much small. So beta like much smaller than 30. So therefore, we go to next page. That's what I wanted to just go back to recap, like putting things all together. You can no longer say, oh, can I still assume beta infinity and then assume it's saturation? I do all the calculations. That's not okay, because you cannot do that. Okay. Any questions? Okay. So if no, then we're gonna go ahead and do a couple more examples. Let me see. Yeah. Yeah. So these two examples are really interesting. So this is a circuit. You're going to see this quite often. They have two resistors at the base in series, and then also they have resistance at the emitter and also resistance at the collector. To do this problem, there's an easy way, like approximate way, and there's also accurate way to do it. So let's start with the simplified approach. The simplified approach basically saying that beta is infinity. Okay. So if beta is infinity, what it tells you that IB is going to be close to 0. If IB is close to 0, you can see what's the relation between RB1 and RB2. They become in series, right? But if this current is not 0, they are not in series because there's branch coming out. So if IB is 0, and then they're in series. If they're in series, this is the voltage divider, right? So, and then it becomes fairly easy to do the analysis. So I'm going to start with simplified calculation. So assume beta is infinity, and then RB0, and then RB1, RB2 in series. And then if they're in series, they become a voltage divider. So therefore, we have VB equal to times 15 volts. That becomes 5 volts. So if that becomes 5 volts, and you can see that this circuit again is not going to be, it's not going to be in cut off, because otherwise you would have VB equal to 5 volts, right? So because now it's in, you assume in active mode. So this is a process. If I assume the active mode and VBE 0.7, so VE becomes minus, no, not minus, VBE 0.7, so VE becomes 5 minus 0.7 becomes 4.3 volts. So you can calculate IE equal to 4.3 divided by 3 kiloohms. It's like 1 point something, 1.43. Now, because we assume beta is infinity, like every step is continuous, so IC equal to okay, so now we're going to say, I'm going to look at VC. So now I'm going to look at VC is going to be 15 volts minus RC times IC, which is 15 minus 5 times 1.43. So it's 5, 7, so it's about 7 point some volts, maybe 7.8 volts. So VC minus VE becomes VC is 7.8 and VE is 4.3. So it be 4.3, so it becomes like a 3.5 volts. So which is larger than 0.3, so it is inactive. Now, of course, this calculation started by assuming beta infinity, and then we got then we calculate all these voltages and currents, and eventually we confirm that VCE is larger than 0.3, so it is in active mode. So nothing is actually wrong in this process if our assumptions is correct, right? So it's okay. But of course, it's not accurate. It's not wrong, but it's not accurate. The reason is the beta was given to be 100. So if you want to actually go back saying, well, if beta is 100, how do I do this problem? There are 2 ways to do it. One way is to follow the procedure we had from last problem, is doing some nodal and then loop analysis. Another way is to convert this circuit into Thevenin's equivalent circuit. Okay, so I need to go back to this circuit over here. Do you guys see this circuit like this one? This one has a 5 volts and a resistance at the base. And we did this example quite easily. But the reason I want to come back here is that if I give you any circuit, right, and you can convert it into a voltage source, I'll do it this way. So for any circuit, linear circuit, we can convert this into a voltage source plus a resistance. Thevenin's, right? You guys remember this, right? And then we call this RT, we call this VT. So do you guys remember how we do this? How to get Thevenin's equivalent circuit? Is basically you take these two terminals, you start to like short the voltage source, open the current source, you look at the total resistance. So that's your RT. And then to get the voltage, you simply solve the actual circuit to find the open circuit voltage over here. So this actually is your VT and the resistance. So if I have so what would be the equivalent circuit? That RT or RTH, VTH.
It would just be RTH would be a 100K and our VTH would be 15 volts.
No.
For those two leads, those two.
Yeah, for those two leads, how much is I mean, this is the equivalent circuit of this. That's called Thevenin's. So, well, first of all, if you want to get the resistance, what do you do? Short the voltage, open the current. We don't have current, so we short the voltage. If you short the voltage, you look from here, what do you get? Like this is short circuit. So you look here, your current comes here, and one goes this way, one goes that way. What do you call it? Parallel, right? Yeah, so RB1, RB between parallel. So this RTH gives you, is going to be and in this case, of course, it's 50 times 150. And can you guys find out how much that is? It's going to be 33. 33, okay. Okay, and how about voltage? Well, voltage basically, you would solve the circuit and simply find the open circuit voltage over here. But there's nothing connected here, so these two are in series. So therefore, it is a voltage divider. And the voltage over here will be how many volts? 5 volts, right? So you got 5 volts. So VTH is 5 volts. So basically, what we are saying is VTH is equal to RB2 or RB1 plus RB2 times that's good 5 volt. So that's the equivalent circuit. So now think about it. If you have a transistor, well, it doesn't matter whether it's transistor or something. Like let's simply do this, which means we can convert this circuit into a voltage and a resistance. Yeah. Here, of course, what I did is I moved the position of this so it doesn't change anything. I just change the order. So for this circuit over here, it can be an equivalent circuit of this. So just the voltage and resistance. So this is what we're going to do for this problem. Let's now go back to this problem over here. So guys, look at what you have on this side is that 15 volts connect to resistance with this output. So we're going to convert this circuit, the left-hand circuit, into a Thevenin's equivalent circuit. So by doing that, we got a circuit. So we start with the right hand, with the left hand. So the left hand becomes like a voltage source and a resistance. And this is, of course, our ground. And then the voltage we got is 5 volts, and the resistance we got. So the rest of the circuit is going to be the same. Okay, so this is our equivalent circuit. Now, if we know this equivalent circuit, this is exactly the same as the one that we did earlier. I mean, the diagram is, the circuit configuration is exactly the same. The only difference, of course, is the resistance is slightly different. So we can solve now this problem on the next slide, the next page. So this is what we have. Yes, what's the difference between what I draw on the previous slide is we simply replace that voltage source like arrow. It's just this is how electronics always do that. So they do that. Now similarly for this circuit, because it's not going to be cut off. Of course, you look at it, you already know. But even if it's not in cut off, it would be hard for us also to solve for IE, IC, IB, and VC and so on, because of the complex relations between all those components. The only thing that we know at this point is VBE is so VBE is going to be 0.7 volts. And if it is in like active mode or in saturation mode, we don't know. So we need to like.
That it isn't in cutoff.
What is it?
It isn't in cutoff.
It's not in cutoff because it's 5 volts. There's 5 volts at the base.
Oh.
If it's in cutoff, VBE becomes 5 volts. Right, so it's not in cutoff. That was easy to observe. So what we can do, we can start assume, okay, so we're going to assume inactive because the previous problem was in saturation, so we solved that one. So now we're going to solve this one by assume it's in active mode. So what we're going to do is, if it's in active mode, we know that IE is going to be beta plus 1 times IB. So that's the equation. So what? So we assume it's in active mode. So VB is 0.7 and IE is beta plus 1 times IB, and beta was given to be 100. So what I'm going to do is I'm going to use this loop analysis. So for that loop analysis, it looks like this. And this is I'm going to do loop analysis on this one. So this is 5 volts. This is 33.3K, and this is 3K. And then this is 0.7 volts. So because we just wrote IE as beta plus 1 times beta, we can also calculate IE equal to like okay, let's do it this way. Let's do the whole loop. So we have VBB is 5 volts. Equal to IB times 33K plus 0.7 volts plus IE times 3K. So I can do the loop analysis because I know the relation between IE and IB. right here, you guys see the loop, right? 5 volts, you got the voltage drop over there, voltage drop across VBE, and voltage drop on this resistor. Two resistors, one junction, and one power supply. So we have VBB equal to IB times 33 times 3 plus 0.7, and then plus IE times 3K. So in this equation, we already know that VBB is 5 volts. So you can plug in the 5 volts equal to IB and then plus IE is better, which is 101, better plus 1 times 3K. So from here, we can find IB. We can find IB is 0.0128. So therefore, I guess you can continue to find IC is better times. So that's 100, so 1.28 milliamps. And
did we say IB? Oh, I think.
yeah, because we plug in IE, we change the IE to, oh, you're right. I missed IB here. Sorry. IE is 101 times IB, so there should be IB here. Yeah. Okay.
We're asking for IE, but
yeah, but we found IB, so now we can find IE. So IE is 101 times, or IB plus IC, so. Or it's like better plus 1 times IE equal to, actually, I didn't get the number. But what I wanted to do is, we need to go back to see if this thing is going to be correct. Sometimes if you just stop here saying, okay, I got an IB, I got an IC, I got IE, I stop. Actually, you might be making a mistake because you didn't verify it is inactive or not. We assume it's active, but we have to verify. So at this point, all we need to do is to find VC and VE. So we can find VE equal to RE times IE. RE times IE, VE is 3.9 volts. Okay. And then we calculate VC is equal to 15 minus IC times RC. That is 15 minus 5 times 1.28 gives 8.6 volts. So finally, we got VCE is 8.6 minus 3.9. That gives you 4.7 volts. Okay. So which means it is in active mode. So we got everything correct. So we don't have to redo it. So by this time, you already see, like, by changing the voltage value at the base and resistance at the base, you can make the circuit either inactive or saturation. It's simply by changing these different resistance values and voltage values. Okay, so let's think about that. Okay, so let's compare like the difference that we had from this one and from the previous one, like assume beta is infinity. So here, our final conclusion was that IC is 1.28 and VC is 4.7. But when we assume it's in when we assume it's in beta is infinity, we got IC is 1.43. So comparing to 1.28, it's like a 0.1 difference, like 10% differences over here. And also VCE is 3.5, but our accurate calculation was 4.7. So that's quite a big difference when beta is not infinity. Okay. So by this point, and also I want to remind you, if it's a MOSFET, there's no current into the gate. So therefore, it will be it will be clear that you don't have to make any assumption at the gate because there's no current anyway, right? Right. So therefore, biasing a MOSFET is easier because when you assume it's like an infinity gain, whatever, then you got this voltage and current, everything was quite accurate. But in BJTs, if we assume it's like a ideal model, we assume beta is infinity, we do the calculation, and eventually we have quite a big difference in terms of VCE. You know, that's 3 point something, that's 4.7, it's almost 1 volt difference between these two. Okay. Okay, so one more example, we're going to conclude our lecture today. Yeah, go ahead.
The next midterm is a week from today?
Yeah. So this is a very typical circuit in amplifiers. So what happened is we need quite a few different types of amplifiers. First of all, usually for small signal, later on you will see, the gain is somewhere between like a single digits and a few tenths. Gain is different from beta, or from like beta is the intrinsic. It is a gain, but it's intrinsic gain between IC and IB. So you can see that you can call that a gain. But often when we design this amplifier with a small signal, what we are more interested is what is output in terms of input. Let's say your input is 1 milliwatt, your output is 5, and then your gain is 5. Right? So that's a voltage gain. So often one stage, like one transistor, is not enough. So therefore, we need to put multiple stages in series. When we put them in series, we get a larger gain. If one stage is 5, second stage is also 5, you get 25. So that's how we get. If you got 3 stages, you get 625 or 125. And another way that we do things is that we also need to try to change the input and output resistance. I think I had an explanation from our very first lecture is how that helps to make use of the input signal when you have like a internal resistance and such like that. Okay. So in this circuit, what we are doing today is to assume beta is infinity, or alpha equal to 1 when we calculate the voltages and currents in each branch. And then except when we want to calculate the IB, we will assume beta is 100. So this is a little tricky. You say, okay, if you assume beta is infinity, would the IB to be 0? Yeah, yes and no. Yes, if we truly beta is infinity, IB is 0. But in reality, that when we often say beta is infinity, we are referring to that between IC and IE. Like IC and IE is equal. So that's what we are assuming for. But anyway, so in this case, let's start analyzing the circuit by doing one by one. So let's start with on this side. So the first BJT is NPN type of BJT. it got two resistors connected at the base. So immediately you might know that, oh, okay, that's very similar to the problem we just did. We can convert this into a Thevenin's equivalent circuit, right?
You don't, assuming I is infinity, so there is no current coming in. So you can just find assuming that that BJT is not in saturation mode, there shouldn't be any current coming in, just seems it B is infinity.
Yeah. So as I said before, yeah, I mean, you can do that. It won't be terribly wrong. It's just not accurate. The reason is there's another word here, except to calculate IB. So that's the tricky part. So which means you cannot assume IB is 0 here. So in that case, our best approach is to start by converting this into Thevenin's equivalent circuit. Okay. And then that will be very similar to the previous example. But there's one difference, is that look at the collector. Now the collector will have, instead of one current, the original current coming this way, you also have a current coming in. So now IC1 is going to be what do we call this? IC1. So I1, let's call this I1, plus IB2. So that is actually a problem, because if you're able to calculate I1, but still IC1 is unknown because it's IB2 coming into this node. So that is a problem. And then finally, for the last circuit, for the PNP type BJT, we would be able to find like IE2 and IC2 if we know either the voltage at the base or if we know the voltage between VEC. But unfortunately, we don't know either of them. So therefore, even the last circuit looks simple. And even if you assume beta is infinity, which means if you assume IE2 and IC2 are the same, you still won't be able to find them because we don't know the voltage at the base for that PNP. Okay. But certainly, if we assume, if we get rid of this, okay, if you assume beta is infinity, let's do that. Just assume it's infinity. And then this circuit will become much easier to analyze. So again, it won't be terribly wrong, but it won't be accurate. However, I do want to do that to illustrate that, a simple step to go through this. Okay, so if we assume beta is infinity, now truly beta is infinity. Now this is voltage divider. So you guys do it together. How much will be, like, let's do step by step. How much is the voltage at the Q1, base of Q1? It should be 5 volts, right? So 150K in series, and the supply voltage is 15, okay? And then this 0.7 between base and emitter. So how much voltage would you find at the emitter of Q1? So 4.3 volts. And then the current of IE1, we can find is 4.3 divided by RE. We'll get some sort of number. And it becomes, because IB2 is also 0, right? Because I assume beta infinity. So IC1 equal to IE1 equal to I1. And therefore, we have we can have VC1 equal to 15 minus IC1 times RC1. So it's a 15 minus IC1 is roughly 1.33, 1.
Well, have we proven that the other one is in that this final one is in
Saturation.
in
Yeah.
saturation or active?
We actually assume all of them in active right now. So I can say assuming active. This type of circuit actually pretty much 100% sure they're going to be inactive unless the circuit was designed wrong. Otherwise, it wouldn't be in saturation. Okay, anyway, so we find VC1, and you know that VC1 is actually equal to VB2, right? So now we can find VE2 equal to VB2 plus 0.7. And then the final step is to calculate IE2 equal to 15 minus VE2 divided by that RE2. So you just by assuming beta is truly infinity and remove the sentence, everything is actually correct, and you can just go ahead and do all the problem. But if we go back saying, well, except for calculate IB, which means for IB is not, well, in fact, if we assume beta is 100, we can still do the problem. It's just a little bit more complex. If we like this is already okay. This actually it didn't give you the step, but it's actually the solution. So the first step will be converting Q1 into the first step is converting this circuit into this. And then based on here, you can write this loop equations. And you can solve for IB1. Okay. This is what we done in the previous example, so we're not going to repeat it. Once you find IB1, you can also find IC1. Okay. And then the second step will be to find the voltage at the base, which is VC1 or VB2. To find that, we have to write another loop equation. See, the current over here is given. So that's IC1 is found. And what we need to do is we will simply write the loop equation on this one. So we'll write the loop equation over here. Because this current we already solved, right? So this current plus this current gives you the current over here. So 15 volts minus the current voltage drop is the voltage over here. And this voltage plus 0.7 gives you voltage over here. And this 15 volts minus voltage here gives you the current over here. And the current over here and over here is relation is beta plus 1. So basically, you can write this part of the equation, and eventually you would solve for all the parameters. That's how we got the final example. Now, of course, this is an example from the book. You guys should be able to go over it as needed. Okay. So I think let me see, 12. Yeah. So probably I think we're almost done with the chapter. Basically, there's just one more example. It's done. So what this example is telling you, there are two transistors. One, like this is a typical like a power amplifier in the future. That you have one power supply to both of the base, and then you have here connect to minus 5 volts, and up is positive 5 volts. If you vary this 5 volts, like the base voltage, these transistors can go into different modes. For example, if this is 5 volts, what would you get? Which one is going to be like in active mode or saturation mode, or which one is in cutoff mode? Like we start, if we assume Q1 is on. So we're not going to go detail whether it's in cutoff or saturation. Whether it's active or saturation. We're just going to see which one is on, which one is off. Off means cutoff. On means it could be in saturation or in active. So if we assume Q1 is on, and also we assume like start by assuming beta is infinity at this point. Now of course it says beta is 100, but here I just want to get started with the problem. So if beta is infinity, so IB is 0. So which means this is 5 volts, this is 5 volts. And if you assume Q1 is on, what will be voltage at the output? No, 0.7. It's going to be 5 minus 0.7. It's going to be 4.3 volts. So if it's going to be 4.3 volts, what happens to the bottom transistor? So VO equal to VE2 is 4.3, which is less than VB2 is 5 volts, which means that Q2 is actually in cutoff mode. Yeah, cutoff. Okay. Yeah, so Q2 is in cutoff. So you might say, okay, well, that's how you made the assumption. What happens if I assume Q2 is on? Would it change? If we assume Q2 is on, and then let's do this. Oops, darn. So if we assume Q2 is on, what do we get at the output? So this is 5 volts, and so this will be 5.7 volts. Right? So VO is going to be, no, VO is going to be 5.7 volts. And so VO is 5.7, and VBQ1 is 5. So what we found is that which is larger than VB1, which is 5 volts, which is also impossible, which means Q1 actually is off. You guys see the problem here? Is that if we assume beta is infinity, and we assume like Q1 is on, and we got Q2 off. If we assume Q1 on, we got Q1 off, which seems to be both correct. So there is a problem. So I want to leave this problem for you guys to think about it, and then we're gonna continue the discussion next week. Next week, Tuesday. Okay.